So one of the things you are likely to get a question for is to sketch a titration curve. There's some really important points that we have to be able to identify. We need to be able to work out what the initial pH is, so what pH we started with before any of what's in the burette is added to what's in the conical flask, so before it even starts. You need to identify what volume is the equivalence point, when the same number of moles of base and acid are present. So when that, what we call equimolar, same molar amount. All right, what volume will that be? You also need to find, therefore, once you've got that, what half of that is, what we call the half equivalence point. And the reason for this is very important. At half equivalence point, the weak acid and its conjugate base will be in equal concentrations. They'll also be equimolar at half equivalence. So we were working with buffers in our past bit of learning. That means that at the half equivalence point, if those two are identical, the acid and its conjugate base, then its pH will equal its pKa, which you'd be given in the question. We also need to find out what concentration it's going to sort of head towards, and then to get our excellence, we may have to work out mathematically what the pH is at equivalence point, because it won't be 7. Unless it's a strong acid and a strong base, which it won't be, then we have to work out that as well. So there's quite a bit of maths involved. So I'm going to break it down into a few different videos because otherwise it gets a bit tiresome. This first one is going to be, what is the initial pH? So what is this value here, the first point in here? And sorry, I've missed some details over here. Let's say for argument's sake we're going to use 20.0 mils of our ethanoic acid to start with. Now that volume is irrelevant for this bit, but it will become important later. The other bit of information that you'd need to be given, or would be given, is that the pKa of ethanoic acid is given as 4.76. Alright, so you've given quite a bit of information. Before we started the video, we had a really quick chat, so I expect a quick answer here. We need to know what's in that solution before I even put one drop of this sodium hydroxide there. So, we talked about that, and what did we say was going to be present in this solution? Clearly ethanoic acid, because it's ethanoic acid. So I've got that present. What else? I've got water. Anything else? Ethanoate ions. You're doing this wonderfully for me too. Hydronium ions, and there was something else as well. And there'll also be OH minus. Okay, I'm going to get rid of that straight away. The reason we get rid of hydroxide straight away is because being an acid, acidic solution, this will be quite low. So I can't really show it in a chemical equation. If I was working with a base, I'd wipe out my hydroniums. Alright? And I can show the relationship between them quite conveniently. You all played that beautifully into my hands, so thank you for that. You know, I think we rehearsed it to do this. Okay, so next thing we're going to do is we're going to work out, well, we've met this before. This is just finding the pH of a weak base. It's a skill we've already done. So let's just go through the process. If I've got an equilibrium equation, then I can write an equilibrium expression. Because it's making hydroniums, what type of K is this? Ka. So I can write Ka equals, and I've got these two here. Over this one here. Water removed because its concentration doesn't change enough to affect this. Now, because no base has been added, I can make an assumption about the things on the right-hand side of this equation. What is that assumption? They're the same. So I can rewrite this as H3O plus squared over. Now I can also make another assumption because ethanoic acid is a weak acid. What will happen to that 0.450 moles per litre? Good, it won't decrease by much, not enough for us to change that number in this equation. So I can make that 0.450 moles per litre. Cool. And I actually know my Ka by manipulating this number here. What would my Ka be?
10 to the negative.
Brilliant. 10 to the negative 4.76. Okay, and we can type that in our calculator, it just isn't a valid number. We rearrange this to find our hydronium concentration. And I'm going to need some help with that if someone's got a calculator handy, please. And then if we can do the negative log of that answer, please.
2.55.
Cool. So I now have the first point on my titration curve. And so this first point at volume of sodium hydroxide, which is what that would be, equals 0. This value, our first important one, is 2.55. So this is where my thing will start. As soon as I start adding any sodium hydroxide, I will create a buffer solution because it will start increasing the concentration of this, and as a consequence it will decrease the concentration of this from Le Chatelier's principle. If this goes up, the reverse reaction will be favoured in here, so that will drop. A decrease in that will increase, so there'll be a sudden increase in pH here, and that's what we're going to look at in the next bit.